Okay, let's get started. My screen is visible and my voice is clear, right?
Yes, sir.
Yeah. Okay, so the syllabus for quiz 2 is week 5 to week 8, as has been communicated to you. In this session, we'll take up concepts from week 5 and 6, and in the next one, that's tomorrow, I'll cover 7 and 8. This will probably get over behind schedule, as in before 10 o'clock itself, it might get over. So if you have any specific doubts, any specific problems or doubts that you need addressed, keep it ready. After I cover the theory, we can take them.
So at the end, you will address doubts.
Yes, specific doubts, if there are any, I'll take up after I cover whatever the main
And
points in
okay,
theory
and
are.
it will end on 10 p.m.
10 p.m. is the maximum that we'll go for, but maybe
Okay,
it'll end before that. Yeah. Okay. So the
that's
first topic in week 5 is that of null space of a matrix, nullity of a matrix, and how to calculate null space and all that. This is something related very closely to the things that we have seen way in the beginning, solving a system of linear equations. So given a matrix, all the vectors such that AV is equal to 0, this set is called the null space of the matrix. In other words, it is just the solution space for the homogeneous system of equations for which A is the coefficient matrix. Now, how to solve a homogeneous system of equations, whether it is a square coefficient matrix or a rectangular coefficient matrix, that is known. Just do row operations, get it into the REF, and then there is a algorithmic way to go about doing it. So this, why do we have this specifically as the null space? This will become clear when we address linear transformations and so on. But first, just in the language of vector spaces that we have developed so far, the first thing to notice is that this is a subspace of Rn. So where do these vectors lie? The solutions to AV equal to 0. The V has to be in the n-dimensional Euclidean space, Rn, this n. So just one. Yeah. This n is where the vector V will be. So if you collect all the vectors which satisfy this equation AV is equal to 0, then you'll get a subspace. To see that it is not very difficult, what are the two things that need to be verified to show that something is a subspace?
the closure under addition and scalar multiplication.
Yeah. So if we take up closure under addition, for instance, what does that mean? If V1 and V2 are in, okay, let me say that this is denoted by N of A. Okay. And if V1 and V2 are there, what does it mean? It means that AV1 and AV1 is equal to AV2 is equal to 0, the 0 vector. Consequently, we'll have A of V1 plus V2. Just by distributivity, this will also be 0, which is the same as saying V1 plus V2 is in the null space. Similarly, you can do the scalar multiplication also. Closure under scalar multiplication as well. So this happens to be a subspace. And many of the examples that we have been dealing with, even when calculating dimension of the vector space and all that, is the null space of a certain matrix. So that there are numerous examples where we take up spaces like x, y, z in R3 such that x plus y minus z is equal to 0. I'm just taking an example. So what is this? This is actually the null space of some homogeneous system of equations. Here there is only one equation, so your coefficient matrix will just be 1, 1, minus 1. So this I can rewrite as 1, 1, minus 1, x, y, z is equal to 0. 0 meaning 0. Yeah, in this case, it is actually just 0. But if you have more equations, let's say it has to satisfy this and this, something like this. Let's not do that. Yeah, something like this. Then this would also be a subspace. If you have a system of equations, the solution space of that is a subspace that we know. So this is a subspace is clear. And then, so once we have any
Is sub
subspace,
is subspace and like is null space and solution space in the same?
so the null space is another name for the solution space of the system of equations for which A is the coefficient matrix. And
Okay.
both of them, I mean, that is a subspace. That is a vector subspace of Rn.
And null space is placed opposite of column space.
I don't understand what you mean by placed opposite of.
Situated.
In what sense?
In a geometrical sense.
Not
Like
really.
how would you? Actually, I
The
have in that.
null space and column space, their dimensions are complementary to each other, as we will see in the rank nullity theorem. But geometrically, they
Okay.
don't need to be situated in any this thing. So because first of all, the null space is in Rn and the column space is in Rm. So they need not even be in the same space.
Okay. Okay.
Right? Column space is the, if you have, let's say, a 2 cross 3 matrix, whatever it is, 1, 2, 3, something, minus 1, 0, 6, whatever. The null space of this will be a subspace of, what will it be? Subspace of?
R3.
Yeah. But the column space, I'll just write it as C of A. This is what? This is the span of the columns of this matrix, which are all in R2. So here, it does not make sense to say it is situated opposite or things like that.
Okay.
When you study
Got
things
it.
like 4 fundamental subspaces and all that, you'll see some relations between these things. But for now, you don't need to worry about all that.
Okay.
All right. So this is a subspace, and the dimension of that subspace is what we will call nullity of the matrix. So nullity is a number which is, in general, let me call this thing as nullity. A is less than or equal to n. You can have zero nullity when your system has no non-trivial solutions. Then your null space itself is just the singleton set. In that case, nullity will be 0. And if you have just the 0 matrix, then the nullity is n. So both extremes are possible. In certain cases, they are not. So such problems you'll probably see. Now that we understand what the null space is and what the dimension of the null space is, let's see how we actually are going to calculate it. So first of all, let's see how to calculate nullity. You are given a matrix, you want to calculate its nullity. So what you have to do is find the number of independent variables for the corresponding system of equations. But how do you find the number of independent variables?
Using REF.
Yeah, so you take you take the matrix, use row operations to get it to the row echelon form, and then the number of pivots is actually number of dependent variables. So the others are independent variables. So let's take an example. Let's take something 3 cross 4, maybe just randomly write stuff. So if I want to calculate the nullity of this matrix, I'll have to reduce this to REF or RREF. REF and RREF doesn't make a difference in the context of finding the nullity. So I'll leave the first column as it is, add it to, I can't add that, multiply the second column by -1, and then remove 4 times, which will give me, yeah, if I make a mistake, let me know. This is still not in REF. If I add 7 times now, here I'll get a 0. Minus 16 and minus 24. So I'll just write it as 1 and 3 by 2, I believe. You know, whatever it is. The thing is that once you get the REF, getting the REF should be routine by now. You look at the pivots. Where are the pivots situated? In columns
all the
1,
three
2, and
rows.
3. So what are the, so there are how many total variables over here?
4.
4. Now, which ones are independent among them?
X1, X2, and X3 is
X1, X2, X3, and X4 is
and X4 is independent.
This is just X1, X2, X3, the others, right? So what do we need to look for? We need to look for number of independent variables. If you want to calculate the nullity, you have to look at the number of independent variables. In this case, there is just one. So what is the nullity of this matrix?
1.
1.
1.
So that's clear, right?
Yeah.
Yes.
Okay. Or the second point here says that number of columns in the REF which do not contain pivot entries. In the REF of this matrix, which is the column that does not contain any pivot entry?
The fourth one.
And how many are there?
Fourth column.
Yeah, the fourth one.
X4.
So there's just one
There are
column
one.
which does not contain any pivot entry. Pivot entry meaning the leading or the first non-zero entry of some row. The pivot entries are circled over here. So only the fourth column doesn't contain any pivot element. So there's just one such column. If there were two columns, for instance, if you had if the REF of the matrix itself was something like this, let's say whatever. So this is in REF, right? What is the nullity of this matrix?
2.
Yeah. So you once again recognize
Because we
what are
have
the pivot entries.
two dependent.
You have two dependent variables and two independent variables. So number of independent variables is nullity. Or if you look at it in terms of number of columns which do not contain, I mean the columns which do not contain pivot entries are directly one-to-one correspondence with dependent variables. So it's really saying the same thing just in a different way. So these 2 points are the same. If this is B, then nullity of B is 2. In this case, it is 2. Okay. Now that is about the nullity. Now about
how do you find a subspace? I mean, null space.
the null space. Yeah, that is what we'll be dealing with now. So first we'll find the nullity. So what does it mean to say that the dimension of the subspace is 2 or 1, or if the dimension of the subspace is n, what does that mean? Just the definition, what does it mean?
This means that
There are n vectors.
N vectors in the space? In the space, there are infinitely many vectors.
n
In the
vectors in the
subspace.
basis.
Yeah, it's in the basis that you have to see. So what this says is that basis of the null space of B has 2 vectors. You can add any basis, has 2 vectors. And if I know how to compute these 2 vectors, then I'm in good shape, right? Because then everything can be written as linear combinations of those 2 vectors. In this case, it is 2, but whatever the nullity may be, if there is a way to compute those n vectors, then every other vector can be written as linear combinations of that. So that is exactly what we'll do. Once again, I'll demonstrate this with an example. So for whatever, so suppose there are k many independent variables. You look at those, the set of all independent variables, you pick one, set it as 1, and then set everything else as 0. By definition, the dependent variables will be determined by the independent variables value. So you will get k many vectors, and that set is a basis for the null space. So an example, let's take the same thing, 1, 2, 4, 3, 0, 0, 1, 3, right? So what are the independent variables here?
The x2 and x4.
X2 and x4. So for the first vector in the basis, what you do is you put x2 is equal to 1 and x4 is equal to 0. And solve the system of equations. So in general, if you what is the set of vectors in the null space? They satisfy this equation is equal to 0, 0. That they satisfy, right? So you have x1 plus 2x2 plus 4x3 plus 3x4 is equal to 0, and x3 plus x4 is equal to 0. Now, in the case that we are considering, we are substituting x2 is equal to 1 and x4 is equal to 0. So what does this give me? x3 is equal to 0.
x3 plus 3x4, right?
Oh, right. Sorry. 1, 2, 4, 3 and 0, 0, 1, 3. Correct. It's x3 plus 3x4. But anyway, x4 in this case it is 0. In this case it is x3 also becomes 0. And if I substitute x3 equal to 0, x4 is equal to 0, and x2 is equal to 1 in the first equation, I'll get x1 is equal to minus 2. Is this okay?
So,
Yes, sir.
from where you
Yeah, is
get
there any
x2, from where you get x2 is equal to 1 and x4 is equal to 0?
That is the method. So you identify the independent variables, you set one of them equal to 1 and all of the others as 0. So substitute, okay, I've written ti, so this is actually xi. So you substitute xi is equal to 1 and xj is equal to 0 for all I not equal to j. That will give you one basis vector. So in this case, there are two independent variables, x2 and x4. First, I'll consider x2 is equal to 1, x4 is equal to 0, and I'll get a solution. What is the vector that I get in this case?
minus 2.
Minus
It's
2,
minus
1,
2,
0,
1,
0.
0, 0. And you can check that this is actually in the null space if you want. If you just want to verify, you can multiply this matrix with this vector, and you'll see that this is an element of the null space. So this is the first case. The second case is x2 is equal to 0 and x4 is equal to 1. So in this case, what will the second equation give me? Once again, this equation is still there. x3 plus 3x4 is equal to 0. That gives me x3 is equal to minus 3. Is this fine?
Yes, sir.
Yeah.
Yes, sir.
And then what would x1 become?
0.
X1 would be 0, is it? 2x2, 4x3. I don't think it is 0.
It's 9.
12 minus 12 plus
It's
3 minus 9. It's 9.
9.
Right. So what is the vector? 9, 0,
9, 0, minus 3, 1.
minus 3, 1. So you have two vectors now. You don't need to verify that they are linearly independent. By the construction itself, they are linearly independent because you take 1, 0 and 0, 1 for the independent variables. Now, if there were more independent variables, what you need to do is you have to consider as many cases as there are independent variables. And in each case, you have to substitute exactly one of them to be equal to 1 and the rest to be equal to 0. And then you get particular solutions, right? So this set, let me call it script B, minus 2, 1, 0, 0, 9, 0, minus 3, 1. This is a basis for the null space of B.
And what is null space of B?
That is what we are discussing, right? Null space is a set of all solutions to the Bx equal to 0.
Okay.
Oh, you want the description of any vector, then you take linear combinations of these two things. Because basis gives you all the vectors. So in other words, I can write B or null space of B as x times minus 2, 1, 0, 0 plus y times 9, 0, minus 3, 1, where x and y are in real numbers.
So null space of B is the span of these two basis vectors.
Yes, yes. That is, basis is the spanning set, right? Is a spanning set for the space.
Yeah.
It's the minimal spanning set. It is more than just a spanning set. You take all possible linear combinations and you'll get the entirety of null space of B. This is not at all different from what you've done in week 2, where you solve a system of linear equations. You get to REF and then you substitute 1 and the other says 0. And if you go back and look at it, it is just solving a system of linear equations. But here we are just changing the language a little bit. All right. Is this clear? Is this algorithm and particular example clear?
Yes, sir.
Yeah, it's clear.
Yeah.
And there can be infinite solution of null space B.
It cannot be infinite dimensional. Like you
I
will
mean,
always
solution.
have a finitely. Yeah. So in this case, there are infinitely many solutions, right, to the system of equations.
Yeah.
If you vary x and y in R, you will get different solutions. So there are infinitely many of them. There are infinitely many elements in the null space of A, which means there are infinitely many solutions to the homogeneous system of equations for which the coefficient matrix is B. But the basis will always have finitely many elements. And that finite number is exactly equal to number of independent variables or number of columns without pivot elements.
Okay, got it.
Yeah. So that's that about null space. Now, when we studied rank of a matrix, which is in, I think, week 4, so you can't really talk about nullity without talking about rank. So here rank comes back. So how do you compute the rank of a matrix? You reduce it to REF and then you look at the number of pivots. The number of pivots is also equal to number of dependent variables. So number of dependent variables is equal to rank and number of independent variables is equal to nullity. Therefore, rank plus nullity of a matrix is, in other words, number of independent variables plus number of dependent variables, which is actually equal to total number of variables. So how many variables are there in a given system of equations, homogeneous system of equations? It is exactly equal to the number of columns. So if I have a 2 cross 4 matrix, then I'll have to multiply it with the 4 cross 1 matrix for it to make sense, right? So number of columns will be equal to number of variables. So this is rank nullity theorem for matrices. The same thing, there's a version of it in the context of linear transformations, which we'll also see later. So using this, there will be some problems. So for example, what is the minimum rank? One way to look at it is if the rank is minimum, the nullity has to be maximum. Or let's say maximum rank for first. So if you want maximum rank, then nullity has to be minimum. What do I want? Nullity is less than or equal to number of columns. So rank is greater than or equal to, like, if I add rank on both sides, rank will be greater than or equal to 0. That's the 0 matrix is the minimum thing. But on the other end of the spectrum, when is rank maximum? That will be when it is the minimum of the number of columns and number of rows. That is the maximum possible rank. Now, this is the case in general, but then in specific examples, you may be given matrices in which there are some values missing, say, or some values not determined. Depending on the value of, let's say, there is some value, something like this, 2, 3, C or something. What are all the possible, what is the possible rank of this matrix? So in this case, it will always be 2 because your first column and second column, they're linearly independent, irrespective of what C is. Then you will have this to always be a rank 2 matrix. And rank 2 meaning nullity is always 1. So in this case, irrespective of the value of C, this will be fine. But if you have something like this, let's say 8, what are the possible values for rank and nullity?
Yes, so rank would be 1 because the second row would be can be a multiple of the first.
Depending on the value of
But
C,
that
rank
is,
can be 1 or 2.
yeah, it could be
Rank
1
can
or
be
2,
2.
right? So rank is equal to 1
It
if,
is 2.
complete this.
C
What
is
should I, how do I
Null
complete
is
this?
2.
If C is 4, rank is 1. If C rank is 2, if C not equal to 4.
Yeah, otherwise. So you can, sometimes it is easier to see how much the rank is, but the things might not be as direct as this. In this case, I've just taken a very simple example where you can readily see that the second column is a multiple of the first column, and the third column is also a multiple of the first column. In case C is equal to some particular value, then you can see that even though nullity could be any value between 0 and n in general, in this case, what is the maximum nullity? What is the minimum nullity?
The maximum nullity would be 2.
Maximum can be 2.
So nullity
No,
is one
maximum could
of.
be 1 and minimum could be 0.
So nullity cannot be 0 because if nullity is 0, then
Minimum can
rank is
be
3.
1.
Rank can't be 3, right?
Yes, yes.
Because the
So if
minimum,
rank is 1, nullity is 2. And if rank is 2, nullity is 1. So in this case, the minimum value of nullity is 1. So using the rank nullity theorem, you can deduce these things. Just using rank, you can comment on the nullity as well. All right. Depending on the value of C, the nullity could be 1 or 2. This is what you can conclude. Now we'll move on to linear transformations, which is the highlight of the linear algebra part of the course. Here we'll study maps which behave well with respect to the operations that we have defined. We started out with a space and 2 operations, plus and dot. And now we ask that we'll study maps for which those operations are well respected. And what do I mean by respected? It is this and this. So if I add 2 vectors and then take the image, it's the same as taking the image of the 2 vectors and then adding them. It does not matter in what order you do it. Similarly, for scalar multiplication, you can scale a vector and then take its image, or take the image of the vector and then scale it. In both cases, you'll get the same answer. So a map that satisfies a function between 2 vector spaces that satisfies both these conditions is called a linear transformation. Now, as a consequence of these two itself, we have the fact that the 0 vector is mapped to the 0 vector. For a linear transformation, T of 0 is equal to 0. So how do we conclude that?
using the linearity property.
Yeah, which property would you use? And
In the first
So-
one, we can have v equal to v dash equal to 0.
yeah, so if I take
Increase
first
the base
property
0.
and then I just do T of 0 plus 0 is equal to T of 0 plus T of 0. 0 plus 0 is just 0. So I just say T of 0 is equal to this. But then if you want, I can just write this as 0 plus T of 0 also. And then there's cancellation law in vector addition. So you will have T of 0 is equal to 0. Or you could use 2 as well. Just put C is equal to 0 and you will get it. 0 times any vector is 0. So you'll have T of 0 is equal to 0 times T of V, which again is 0. One thing to notice, where these operations are happening, you have to be careful about. It will, for most part, not matter because you'll be working in subspaces of Rn. So this is happening in W, and this is happening in V. This plus is of V, and that plus is of W. The left-hand side, the plus is of V, and the right-hand side, the plus is of W. Similarly, scalar multiplication also. If you're doing the scalar multiplication first, which means you're doing the scalar multiplication in V, and then on the right-hand side, you have C times T of V, which is the scalar multiplication, which is happening in W. Okay, so T of 0 is equal to 0 is not an axiom that needs to be stated separately because it can be deduced from the axioms. So, but this is a fact that this always happens. For example, if I have something like T of xy is equal to, let's say, x plus y plus 1, something like this. You can look at the image of, and here, of course, 0 means the 0 vector. In the case of R2, the 0 vector is what? 0, 0 itself. In this case, T of 0, 0 is 1. This is one way of verifying. So this is a necessary condition. T of 0 is equal to 0 is a necessary condition for a map to be a linear transformation. What do I mean by necessary but not sufficient? Is that if I have something like this will satisfy T of 0, 0 is equal to 0, but this is not a linear transformation. So this is something that you need to check. So this is, both of these are not actually. These both not linear transformations. But if you at the first step itself you see that 0 is not mapped to 0, then you can directly say that it's not a linear transformation. All right.
Sir,
Sir,
can I ask something?
if satisfies 0, then what should be the next step?
Then you'll have to actually do things like verify whether T of V plus V is equal to T of V plus V prime is T of V
Like
plus T
both
of V
the
prime.
given properties, addition
Yeah,
and
in this
scalar
case,
multiplication.
take something like this. T of for this I'm saying T of this is T of 2 comma 2, which is 4. But T of 2 times T of 1 comma 1, what is that? That is 2 times 1, which is just 2. So T of 2 times 1 comma 1 is not 2 times T of 1 comma 1. So this is not a linear map.
Okay.
Okay, so now if
Sir,
you want
just
to prove that something is, then you will have to give a theoretical proof of why it holds for everything. To show that it is not, you have to produce an example, a particular vector or a pair of vectors which do not satisfy either of these properties. Yes, there was some other doubt.
sir, does the linear transformation thing has anything to do with the one-on-one and onto? Like it
Linear
has to be
transformation is a
one-on-one.
map. No. Linear transformation as it is need not be one or onto. So take for example the map between any vector space where I send any vector to 0. That is also a linear transformation by definition, because your T of V plus W or T of V or T of V plus V prime, T of V prime, all of these things will be 0. Trivially, both of the necessary conditions are satisfied. So this is a linear transformation. Some doesn't make sense because everything is collapsing to 0. Not doesn't make sense, but it's not interesting because everything collapses to 0. But still, it's a linear transformation. It's neither injective, everything is going to 0, and then not surjective. Only 0 is there in the image. So this is also a linear transformation. But yes, so when is a linear transformation injective and surjective is interesting, and that is why we have the in terms of for linear transformations, at least for injectivity, there is a more specific condition. In general, for a function between two sets, how do you formulate injectivity or one-oneness? You say that T of V is equal to T of V prime happens only when V is equal to V prime. So what does this mean? You have a map between two sets. If you have this to be the image of two different things, if this is not equal to this and both of them go to the same thing, this is not a one-to-one map. So a one-to-one map is a map such that there is only one pre-image for every point in the image. Pre-image meaning a vector which is mapped to that element. This is the formal way of writing it for any function. T of V is equal to T of V prime should happen only when V is equal to V prime. But in the case of linear transformation, we have something better, a better way of checking. Injectivity is equivalent to saying that you just check the pre-images of 0. You just look at what vectors are mapped to 0. If there is only one such vector, which is the 0 vector, right? So what is the pre-image of 0? What is P inverse of 0? As a set, this should at least contain this, right? That is by definition, 0 is a pre-image of 0. But if this happens, this is in set notation, then you have injectivity. And this is a property that is specific to linear transformations. So let us take, for example, again, simple demonstration of the same. If I have something like 2x plus y and 4x plus 2y, clearly you see how I've chosen the numbers. It it makes sure that it is not injective. Now, if you were to use this property that you look at all the pre-images, can you give me a non-zero element which is mapped to the zero element?
One minus two.
So you see that this is 0, 0. In general, if you try to find the set of all values vectors which are mapped to 0, what does it boil down to? It boils down to solving a system of linear equations. 2xy is equal to 0 and 4x plus 2y is equal to 0. You need to find the solutions to this system of equations. And clearly, in this case, there are only two equations, so this will have infinitely many solutions, two equations in two variables, only when one is the multiple of the other, which in this case it is. Now, if you have three variables, you will have to determine using Gaussian elimination, row operations, whatever, whether that system of equations has infinite solutions or just the unique solution. If it just has the unique solution, then it is injective. If it has infinitely many solutions, then it is not. Is that clear?
So please give an example of injective and example of surjective.
Surjective we have not dealt with yet. So you can just take, so in this case, T is not injective. Right? Now let's take another example. The same thing, R2 to R2 itself. I'll not write everything again. Just take something like x plus y, x minus y. Now what is the set of all vectors that are mapped to 0? So suppose
1
T of
minus
x2,
1.
1 minus 1 is not, right? Because it goes to 0, 2. You want it to go to 0, 0. So if T of xy is equal to 0, 0, I want to find all such xy. I'll set up a system of equations because T of xy is x plus y, x minus y. So x plus y is equal to 0 and x minus y is equal to 0 has to happen simultaneously. And what is the solution set to the system of equations?
X equals to 0 and y equals to 0.
So it just has a trivial solution. In this case, since it's a map from R2 to R2, the system of equations that we set up will be one with a square coefficient matrix. So you can also argue using determinant and all that. But anyway, in this case, at least it is quite simple to see that the only solution to the system of equations is a trivial solution. So a common theme that you should notice throughout the course, at least in the linear algebra part, is that most things, if not all of them, come down to solving a system of linear equations. And that's why we have that in the first part, in week 1, week 2, how to solve a system of linear equations. And then whatever problem we have, we translate it into a system of equations that needs to be solved. So injectivity is also checking for injectivity is also solving a system of homogeneous linear equations, homogeneous system of linear equations. All right. So that's about injectivity. Now surjectivity is, what does injectivity say over here? It says that an element should not have more than one pre-image. Let me write that over here. Not more than one pre-image. Here it says every element should have at least one pre-image. So there should not be any vector that is not the image of any vector from the domain. So that is what is surjectivity. And this surjectivity is not anything specific to linear transformation. Surjectivity is the same as surjectivity of a function, just that. But
Sir,
later on
actually,
we'll see. Yeah.
So actually, I know the formula, I know the definition, everything, but I don't know how to proceed to solve.
So in this case, for injectivity, did you understand how to check whether it is injective or not?
Yes, for injective, it should be at least one in pre-image.
At least one non-trivial element in the pre-image of the zero
At most
vector.
one pre-image for injective.
Yeah. If you want it to be injective, then
It
it
should
should
be
be
at most
exactly one. So in this case, zero will always have a pre-image, right? So if we are talking only about the pre-images of zero, it has to be exactly one.
yes.
In general, for functions, you're right. It has to be at most one.
And for surjective, it should be at least one.
It should be at least one pre-image. What does
Yes.
that mean? It means that if I set up a system of, once again, when you're given some linear transformation, the components will be linear expressions, right?
Yes,
And
sir.
then you want that linear expression covers the entirety of the image. So the entire W, any vector in W, should be in the column space of that particular system of equations, the coefficient matrix. That's how you check it. But then later on, we'll see how to determine the image of the transformation is something that we'll check for specific, like there's an algorithm to do it. We'll get to that in a bit. But at least in this case, this particular example that we have over here, the simple example that we have over here, what do you observe the relation between the first component and the second component of any image vector?
First, second component is twice of first component.
Yeah, so it's of the form some c comma 2c, right? So for example, 1 comma 3 will never be an image of this transformation, will not be in the image of this transformation. The image vectors will be of the form c comma 2c. So 1 comma 3 will not be there. So at least in simple cases,
Only odd elements.
so if you look at R2 as a, using the coordinate plane description, you will just get y is equal to 2x, the line which is y is equal to 2x. Only that will be the image, line through the origin, something like this. Every other point here, that will not be in the image.
Sir, can we say surjective means range of T is equal to codomain?
Yes, that is the definition of surjectivity of a function. Yeah, that is exactly what it is.
Okay.
Yeah. For example, now if you want to prove that this second example, x plus y, x minus y, this is a surjective function, you take an arbitrary element in the codomain. We want to show that the codomain is the range. So what does an arbitrary element in the codomain look like? The codomain is just R2. So you take any AB, and then I want to see if this is equal to T of xy for some xy. But what does that mean? T of xy is just x plus y, x minus y. So I want vectors, I want real numbers x and y such that x plus y is equal to A and x minus y is equal to B. But is this system always solvable?
Yes.
Can you explain why?
We
X
can
is equal to
express
A plus
x
B by
as
2.
a minus y and y as x minus b.
You need to give x and y in terms of A and B.
X is equal to A plus B by 2 and y is equal to A minus B by 2.
minus b by 2.
Yeah, this is in this particular system. But what is it that allows me to say that this always has a solution? One way to say it is that this is a system of equations for which the coefficient matrix is a square and invertible matrix. So I can just take the inverse on the other side. So as long as that happens, I'm good. And in this case, it is what? 1, 1, 1 minus 1, which is an invertible matrix. So Ax equal to B, if I have a system of equations, Ax equal to, let's not call it B because I've used it. So if I have X equal to C and A is a square invertible matrix, this always has a solution, right? Does not matter what C is. So X tilde will be A inverse of C, or you can use Kramer's rule if you want. So corresponding to every C, I have given an X tilde such that the image of X tilde is actually C. So this is surjective. The second example is surjective. There will be other methods also to determine surjectivity. But even for
how do you know
surjectivity,
it?
yeah, go ahead.
So how do you know? How did you find out that it is like invertible?
So in this case, you have x plus y and x minus y. So how do you write this in the matrix form? This is 1, 1, 1 minus 1 times xy is equal to AB. And this is an invertible matrix, right?
Yes, sir.
Yeah.
Sir,
So
say
that-
had this. So I have a question here. So, for instance,
Yeah.
let's say that had this not been a square matrix, how do you have found out that this is going to be surjective without commenting on the invertibility of the matrix?
Right. You have to look at what the column space is. So if the column space is R2, so suppose this was, okay, maybe let's take an example. Yeah, whatever. Yeah. So suppose now that T of xy is, I want, let's say, a 2 cross 3 matrix. So I'll do something like this. X plus 2y plus z, x minus y minus z, and just z. Now, if I want to verify whether this is surjective, what do I need to do? I need to try and solve the system of, wait, I just want two variables. No? I said I just want two variables. So suppose this is from R3 to R2, and I want to check whether this is surjective or not. For arbitrary A and B, I need to be able to solve the system of equations. What is the coefficient matrix in this case? This is 1, 2, 1, 1 minus 1 minus 1.
1 minus 1.
Right? What does it say? What does it mean to say that an arbitrary element of R2 can be solved? It is the same thing as saying the column space of this coefficient matrix is R2. Let me write that down. T is surjective if and only if the coefficient matrix here has column space equal to codomain. What is the column space of this matrix? It's exactly the range of the transformation. Is that fine?
Yes.
Is this statement clear?
Can you explain?
Yeah, okay. So I have taken the expression over here, x plus 2y plus z, x minus y minus z. I want to know, as I vary x, y, and z, what are all possible values that it takes. It is the same thing as saying, as I vary x, y, and z, what are all possible values that this expression takes, which is the same thing as saying, what are all possible values of this as you vary x, y, and z. But what is the set of all possible values of this expression as you vary x, y, and z? What is that thing called? Anyone? So if I take the columns and take all possible linear combinations, what is it called?
So that's column space of A. Right?
Yeah. So this is exactly the column space of A. So if the column space of A is equal to the codomain. Now, why do I want that? Because I'm looking for surjectivity. I want some linear combination of the columns to be equal to an arbitrary element in the codomain. So if column space is exactly equal to the codomain, then it is surjective. But given a matrix, you know how to calculate its column space. Right? In this case, is the column space the entirety of R2? What is the rank of the matrix?
2.
2.
Yeah, rank of the matrix is 2, meaning what? The column space, the columns are in R2 itself. What is the two-dimensional subspace of R2?
The R2 itself, right?
R2 itself. So the column space is actually equal to R2. So irrespective of what A and B I take, I can solve this equation. In fact, if you want to have more clarity, take this system of equations, write your this thing augmented matrix, and then continue to just take it to its row echelon form. What do I get? I get -3, -2. And I'll just normalize it, divided by -3 to get 1 and 2 by 3, I think. Okay. So I did what? B minus A. So I did B minus A divided by -3. You can do all of this. B minus A becomes A minus B by 3. Just check whether this is correct. But now I can solve this, right? Just keeping A and B as arbitrary constants. How would I solve this? X2 is equal to 2 by 3 minus 2 by 3t plus A minus B by 3. And X1 you can find out using X2 and X3. So X3 I've set as t because X3 is the independent variable for this system of equations. But this is for the particular example. In general, what do you want to do to determine whether something is surjective? You look at the column space of the matrix that you form using these coefficients. A more general method, we'll see. This is the same as saying that look at the matrix of this transformation with respect to the standard basis and then do it. So you don't need to, there is a more general method where you can use any basis. We'll see that.
So there's 3 properties, right, to check surjectivity and injectivity. Like if nullity is 0, then the equation will be 1, 1. Like we have
nullity
3
is 0. Yes, we have not talked about the nullity of the transformation yet. When we get there, it'll.
We have 3 properties, right? Now, m is greater than n, and for n is greater than m, and for m is equal to n.
Okay, you can memorize some specific cases, but the underlying principle is this. What is happening is you are trying to solve a system of linear equations, and in the system of linear equations you have all those conditions, right? If you have a rectangular matrix with more equations than the variables, then you will always have a solution, stuff like that. It is all the same way of different ways of saying the same thing. I don't know what 3 rules you are specifically referring to, but it should be a consequence of these things itself.
Okay.
All right, so is this at least somewhat clear?
Yes.
So how did you write that x2 equals to minus 2 by 3t? What is the t here?
Okay, so x3 is an independent variable, right? So let us do that one step, since we're doing this anyway. So I have x2 plus 2x3 by 3 is equal to a minus b by 3. This is what this second equation gives me. Is that correct?
Yes, sir.
Yes, sir.
So I write x2 is equal to minus 2x3 by 3 plus a minus b by 3. So this x3 I just substitute as t because I can take any value. By taking different values of t, you will get different solutions. Since it's an independent variable, I just kept it as t. And for different values of t, it will determine values of x2 and x1. If you now write the first equation, which is x1 plus 2x2 plus x3 is equal to a, and then substitute the values of x3 as t and x2 as minus 2t by 3 plus a minus b by 3, you will get something like an affine subspace description of the thing, of the solution space in terms of a and b.
So what will be the value of x1 b by 3?
No, you'll start out with x1 plus 2x2 plus x3 is equal to a. That is what I get using this. And then substitute x3 is equal to t and x2 is equal to the thing that you obtained earlier. This. And then simplify and you'll get it. I don't know exactly what it is, but you'll get it in terms of t, a and b.
x3 is equal to 2 by 3t.
x3 is just t.
Just t. Okay.
Because that is the independent variable.
Because it's independent. That's why.
Yeah, I just substitute as t. You can keep it as x3 itself.
Okay.
You can write it in terms of x3. You can get the solution in terms of x3. All right. Okay, so that's that. Where were we? We were doing injectivity, surjectivity. Now, another important property of linear transformations is that in order to understand the transformation, I just need to understand a finite number of vectors. And what is that finite number? It's actually equal to the dimension of the domain. So if I have any basis v1, v2, vn, then the images of those. So if I say I know the image of a basis, then I essentially know the entire transformation. And this is due to the linearity properties of the transformation. And a quick outline as to why that happens is any vector can be written as a linear combination of a basis, uniquely as a linear combination of basis vectors. And then if I apply t on both sides, the linearity properties, the plus and the plus gets distributed, the scalars come out, all of that happens. And okay, here there needs to be a t of. So, but t of v1 to t of vn is what we know. If we know t of v1 to t of vn, t of v for any v, we can determine. Is that clear?
Yes, that's from the linearity property, right?
That's simply because of the linearity property. Once again, for a simple example, if I know that t of 1, 0 is equal to, let's say 1, 1, and let's say t of 0, 1. This is a standard basis. You don't need to have the standard basis. You can do it with any basis. Let's just do this once. If t of 1, 0 is 1, 1 and t of 0, 1 is 2, 1, what is the general expression of t of xy? So I'll give you guys like 2-3 minutes. Just compute and let me know. If someone is done, you can just speak up.
Be x plus 2y and x plus y.
Could you repeat that?
And that be x plus 2y and x plus y.
3x plus.
Yeah, it will be x
1.
plus 2y.
It's x plus 2. Yeah. And x plus y.
Y. Yeah.
Yeah. Does everyone understand why this happened?
Can you please explain once?
Yeah. So if I take any t of xy, I can write it as t of x times 1, 0 plus y times 0, 1. And I'm just writing xy as x times 1, 0 plus y times 0, 1. This is just the properties of. I'm just splitting the xy. Yeah, I'm writing the xy in terms of the standard basis. So this is what you would do for anything, but then you'll have to determine the coefficients. That is another intermediate step that you'll require for a random basis. But anyway, in this case, the standard basis, the expression is easy to see. So because of linearity of t is a linear transformation. So I'll get x times t of 1, 0 plus y times t of 0, 1, which in turn I can now write as x times t of 1, 0 is something I know, which is 1, 1 plus y times t of 0, 1 is 2, 1. And then I simplified. What do I get? Is this clear?
Yes.
Yes, sir.
So this step to this step, in this case, it is easy. But if suppose the basis was something like 1, 1 and 3, 4 or something like that, you'll have to determine how to express any xy as a linear combination of that, which is once again solving a system of linear equations, and it is guaranteed to have a solution.
Is there a reason why we are using xy's? Because C1, C2s are the coefficients, right? Is there any reason why we are using xy? Or?
No. There's a C1, C2 or xy. It's
the same,
just,
right? Yeah.
Yeah, it's just a difference in naming. Yeah. In general, the points of R2 we use xy. R3 we do xyz, and more than that we generally do x1, x2, x3, x4.
Okay.
And then when we split it, it just happens to be, in this case, the coefficients happen to be x and y.
Got it.
So yeah, if I know the image of a basis, I know the transformation. So this is another powerful property of a linear transformation. So you just need to have a finite set of numbers and you know the entire transformation, which is not the case for a general function. If I have, say, y is equal to x square, or suppose you don't know that it's y is equal to x square, and you're just told that you have a function and you give me finite number of values, then I cannot recover the function from there. But for linear transformations, it is possible, and it is because of the linearity properties.
For y square, you could not do that because it's simply not a linear function, right? That's not possible.
For suppose your function is f of x is equal to x square. Now you don't know that this is the function, but you are just given a set of points, let's say 1, 1, 2, 4, 3, 9, whatever. Suppose you are given these 3 points. You cannot say that this is necessarily coming from this function. There could be other functions which with the same observation. right? I cannot think of a function which once again satisfies this, but I'm sure there are. Yeah, you can cook up functions, but in case it is also known that it is linear, in this case you will not have any linear thing which will have this as the observed data. But if it is more dimensions and it is known that the data points they behave in a linear manner, then you can recover the transformation just by using the basis number of, or the dimension, or you want to call it features. The features number of data points will be sufficient to determine the whole transformation.
Excuse me, sir.
Yeah.
So there you have used the standard basis 1, 0 and 0, 1.
Yes.
Is it like if we are not given any basis, only then we will use this basis, or?
So if you want to recover a transformation from the image of the transformation on a basis, you will be given a basis. It will be like, instead of 1, 0 and 0, 1 over here, you will have some other values. And as long as it is a basis, every vector can be expressed as a linear combination of those things. And you'll have to make changes accordingly.
Okay.
I'll maybe give an example at a later stage where it is not the standard basis.
Yeah.
If we
please.
finish it in time, we should, and then we'll take it there. Okay. Now that we know what is injectivity and surjectivity, when a transformation is both injective and surjective, it is said to be an isomorphism. And in general, when you talk about certain structures, may it be vector space or something else, determining when two of the objects in the given category are same is a very important question. In the category of vector spaces, we have linear isomorphisms. Now, this does not mean that, okay, suppose I have two vector spaces and there is a linear isomorphism from V to W, then it is said to be isomorphic. So for all purposes, we'll consider them to be the same. It is just a different naming system kind of a thing. So for all vector space purposes, those two spaces will be the same. Now, if two vector spaces are isomorphic, this of course does not mean that every map between them is an isomorphism, because whatever vector space you take, you can just take T from V to W where everything goes to 0. That is always a linear transformation, as we had seen earlier. And that will never be isomorphism unless V and W both are trivial. But that is the least interesting thing. So it does not say that every map from V to W is a linear isomorphism. What we require is that there is at least one map between them, which is a linear isomorphism. That as a definition makes sense, right? It is injective and surjective, means every element is mapped to a unique element and every element has a free image. All of that, it makes sense. But given two random vector spaces, how do you actually check if there is a isomorphism between them? Like how would you go about can you consider all possible maps and check one by one? That is not practical. So the practical way of checking whether or not two vector spaces are isomorphic is to just compare their dimensions. The proof of this I will not give. I think it is given.
First, we should see their size.
Size, if by size you mean dimension, yes, you have to calculate the dimension of the two vector spaces. If they are same, then an isomorphism between them is guaranteed. If the dimension is not the same, there can never be an isomorphism.
But if their dimension is same, but it is not injective or it is not surjective then?
So you are not given a transformation, right? You are just given two vector spaces and you are asked whether or not these two are isomorphic. What does this mean? It just means, does there exist a map between them which is an isomorphism? In case their dimension is the same, the answer is yes. There is a map which is an isomorphism. There could be other maps which are not isomorphisms also, but at least one isomorphism is guaranteed. That's what it means. Is that fine?
Yes, sir.
So that is when they are said to be isomorphic. Yeah.
So
So
what
the
is it?
second.
So
Yeah,
I
go
have
ahead.
a simple question. Like, what does it mean when we say that a vector space is given to be is up to some isomorphism when we say? So what does it mean to be that, like, up to some isomorphism?
I don't think you have encountered that terminology in this course. Maybe in
Yes,
some
I mean,
textbooks you have read
yes,
read
yes,
that.
yes.
Yeah. So up to isomorphism means that. So let's say it goes along the lines of up to isomorphism. It is unique. It means that whatever answer you get at the end is isomorphic to V. It need not be equal to V. Without specific examples, it's a bit difficult to explain. Yeah, and honestly, in the context of this course, it is not required. So I'll skip it for now. Maybe if you can maybe tell me in what context you read it, and then I'll explain it to you.
Yes, so I was reading this book by Kenneth and by Hoffman and Kuhn. So
Okay.
they were writing this. I mean, very colloquially, that this up to some isomorphism, this is fine and so on. So I was like, is this vector W when we say that it's up to some isomorphism, does it mean that the vector space W is isomorphic to V, or there is a map which is up to some isomorphism good to
So up to
specify?
isomorphism, this is the vector space, meaning you will get a vector space which has the same dimension as this. That does not necessarily need to be equal to it.
Okay.
Yeah, I think we'll leave it at that for now because it's not entirely relevant to the others. So, right. Now the third point over here will make sense after we look at the last comment of this session, which is the rank nullity theorem. But it is good to have it as one of the usable tools. That if you have vector spaces of the same dimensions, then so as I said before, even if they are of the same dimension, any map between them need not be an isomorphism, right? You could have non-isomorphic, non-linear isomorphism transformations between even isomorphic spaces. But in case you know that the dimension is equal, then instead of having to check both injectivity and surjectivity, checking one of them is enough. So suppose I have a map from R3 to R3. It's a linear transformation. So T is injective if and only if T is surjective. So this is a specific example. Why is this the case? We will see when we talk about rank and nullity of the transformation. But this is true in general for same dimensional spaces. For isomorphic spaces, a transformation between them is injective if and only if surjective. So whichever seems easier to check, you can check and just say that the domain and the codomain have the same dimension. So the other thing also holds.
Sir, by intuition, can we say that if dimension of V is less than dimension of W, then they will not be surjective? Like, intuitively, can we say like R2 will have less elements compared to R3, so they cannot be surjective like that?
Yes, you could R3 to R2 or R2 to R3.
R2 to R3.
Yeah, R2 to R3, you will have more elements in the codomain, right? You cannot, yeah, in some sense, you cannot cover R3 with an R2.
So can we generalize that if dimension of V is less than dimension of W, then they can never be surjective like that?
Yes, let's keep this as an exercise for now.
Okay.
If T is V to W, and what is the thing that you said? Dimension of V is less than, let's say strictly less than. Because if it is equal, of course, you'll have an isomorphism. Then what is the conclusion?
T can never be surjective.
T can't be surjective. So this is your intuition, right?
Yeah, based on number of elements in R2 and R3.
Well, I wouldn't call it number of elements, but okay, yeah, I understand what you're saying. And that intuition is correct. And we'll prove this at the end.
Okay.
So I've heard something like that too, but it's like if you go opposite, like R3 to R2, then it can't be injective like that.
Dimension of W is less than dimension of V. Then T can't be injective, right?
Yes, sir.
Yeah, we'll try to prove both of these at the end. Now comes matrix of a linear transformation. This is, I think, something which people have a bit of difficulty, at least historically, that's what we have observed. So how to write the matrix of a linear transformation with respect to given basis? When you have a linear transformation, you have a domain, you have a codomain. Both of these are vector spaces, meaning both of these have basis. Now, basis is not unique. I could take the standard basis 1001 on, or whatever standard basis, if it is even Euclidean space, right? And I can have the standard basis on the codomain as well, if that is also Rn for some n. But that is not the only choice of basis. So the matrix of a linear transformation is something which is dependent on a choice of basis. All right. Given a linear transformation and a choice of basis for the domain and the codomain, we can construct what is called the matrix of the linear transformation. Now, what is the size of the matrix of the linear transformation? Dimension of the codomain times dimension of the domain. That is the size of it. And how do I get it? I look at the images of basis vectors, express it in terms of the basis for the codomain, and write down the coefficients as columns. Now, for this, let's do an example with a non-standard basis. We'll do standard as well as non-standard. Let's do R2 to R2 itself. Let's say xy goes to whatever we were doing earlier itself, x plus y, x minus y, or I don't know, maybe I did x minus y, x plus y, it doesn't matter. Now, suppose the basis on the domain is this, and basis on the codomain is this. Standard basis for both. So this is the easier part. So what needs to be done is look at the image of basis vectors for the domain. In this case, what is t of 1, 0?
It's 1, 1.
It's 1, 1. Now this I have to express in terms of the basis vectors for the codomain. In this case, it is easy because I can write this as 1, 0 plus 0, 1.
1 times 0, 1, right?
Yeah, that's just 1 times 0. And t of 0, 1 is 1 minus 1, which is 1 times 1, 0 plus minus 1 times 0, 1. Right? Then you have to look at these coefficients. So the matrix of T. Now this is not a notation that is used by the prof, so I'm just doing this to emphasize that I'm using the matrix of the transformation T with respect to the basis beta 1 and gamma 1. The first column will be the coefficients of the first basis vector, image of the first basis vector. In this case, it is 1 and 1. What is the second column? That will be 1 and minus 1.
Sir,
Yeah.
so how do you get t of 1 comma 0 is equal to 1 1 and t of 0 comma 1 is equal to 1 minus 1?
The definition of T. What is the definition of T?
X plus y and s minus y.
So what if you substitute those values?
Okay.
All right. 1 1 1 minus 1, and in the standard basis those will exactly be the coordinates also, coefficients also. Now let us take something different. Let's do 1 1 1 minus 1 for both domain and codomain. This might get
So beta
computationally
is your
heavy.
domain, right?
Beta is a basis for the domain, gamma is a basis for the codomain. In this case, I'm taking both of them to be the same. Even in the second thing, I took the thing to be the same, or maybe, yeah, in the third example, maybe I'll do something even more complicated. So what is T of 1 1?
2 comma 0.
0.
This is 2 comma 0. But this is, how do I express it in terms of the given basis?
The 2 1 comma 0. So you want to express in terms of this, right?
But we
So-
want to express it in terms of this.
Yes. So x plus 1 comma 1 plus.
So if
1
I
minus
want
1.
more clarity, let me call this V1, V2 and W1, W2, even though V1 and W1 are the same. You have to first look at T of V1, which is nothing but T of 1 comma 1. This is 2 comma 0 as we saw earlier, but this is once again W1 plus W2, right? I'm writing it as a
Hold on.
linear combination.
Alpha times W1 plus beta times W2, right?
It's
Or-
exactly a W1 plus W2, right?
Yeah, correct. Yeah.
In
Okay.
this case, it is, right?
Yes.
In general, you will have to write it as alpha plus that and then solve for that system of equations. So you have to solve for this alpha and beta. But in this case, I can see. So T of V2 is 1 minus 1. Now, what is one image of 1 minus 1?
0 comma
That is, there is 0 comma 0 plus W2. 0 comma, no, it's 0 comma 2. It's W1
Once
minus
again, we
W2.
W1 minus W2.
Minus
Right?
W2.
So what is the matrix of the transformation with respect to beta 1, gamma 1? Sorry, beta 2, gamma 2. The first column will correspond to what are the coefficients of T of V1, and the second column will correspond to what are the coefficients of V2. So here you will get a 1, 1, here you get a 1 minus 1. It turned out that the matrix is the same. Now, let us do something else where I'll have something like this. I'll take the standard basis for the domain. Once again, I'll call it V1, V2. For the codomain, I'll take this basis, 1, 1, 1 minus 1. Now see what happens to T of V1. What is T of V1? As we had calculated earlier, this was just, okay, let me call this W3, W4. It's still W1, W2, right? Okay, maybe I should call this guy V3, V4 to distinguish it from the previous case. Let me just call it E1, E2. since it is standard. I look at the image of the first vector in the chosen basis, and that happens to be 1, 1. How do I write 1, 1 as a linear combination of these things?
1 times 1,
W1
0
0
plus
W2.
1 times 0, 1.
So it 1, this thing is correct, but this is not what I want, because I want to express it in this basis, not the standard basis. This time the basis that I've chosen for the codomain is W1, W2, which are not the standard basis. I want to express it in terms of the standard basis. I want to write it as something times W1 plus something times W2. What are those somethings?
1 and 0.
Yeah, so this is 1 times this plus 0 times this. And what is T of E2? Which is
1,
T of 0, 1.
1.
This is 1, minus 1, which I want to again write in terms of the chosen basis, something times W1 plus something times W2. Once again,
0 and 1.
so this is 0 and this is 1. So the matrix, oh, sorry, this has to be beta 3 and gamma 3. It's equal to one of the bases before, but I'll just write it as beta 3 and gamma 3. Now, can you tell me what the
identity matrix?
Yeah. So the first column will be this one and this one, and the second column will be this one and this one. This and this is the second column. All right. So we have got symmetric matrices. So don't arrange the coefficients in rows. It's actually these. This is T of coefficients of T of E1 are these things. Is this clear? How to construct the matrix of a linear transformation with respect to given basis?
Can you give one example where we need to calculate these coefficients like scalars, linear combination when it comes?
Okay, let's do something. Here I'll keep the basis on the domain as the same thing, standard basis, but gamma 4 I'll take to be something wild. Right, so something like 2, 3, 7, 9, something like this. I might not take this calculation all the way through, but I'll tell you what needs to be done. So this is, first you look at again T of E1 because E1 is the first basis vector for the domain. Let's call this W3, W4, something like this. So TE1, what is TE1? That is just 1, 1. But how do I express this as W3 plus W4? Something times W3 plus something times W4. If I have to find these coefficients, what do I need to do? I need to find alpha and beta such that alpha times 2 by 2, 3 plus beta times 7, 9 is equal to 1, 1. Or if you want more familiar territory, you can call this C1 and C2. C1 times 2, 3 plus C2 times 7, 9 is 1, 1. What is this? This is a system of linear equations.
Okay, got it.
Right? You will have something like 2, 3, 7, 9, C1, C2 is equal to 1, 1. Now, beyond this point, I could continue, but do I need to? So here you'll get the C1, C2. Just because this is an invertible matrix, you compute the inverse, you multiply inverse on both sides, and then you get the value of C1 and C2. And that C1 and C2 comes over here. And when you compute the matrix of the transformation, when you write that, you will get C1 and C2 over here. This is the first column. For the second column, what do? You look at T of E2, which is 1, minus 1. which will lead you to solving another system of equations, which is 1 comma minus 1 is equal to C1 times 2 3 plus, or C3 times 2 3 plus C4 times 7 9. And those coefficients, once again, why are you guaranteed a solution in all of these system of equations? Because this is a basis. So every vector can be expressed as a linear combination of a given basis. The basis that I choose might be different, and consequently the coefficients that I get might be different. But what I'm guaranteed is the existence of a solution in such a case.
So is it because it spans the entire vector?
Yes, and it is not just spanning, it is spanning and it is linearly independent. You just don't need some coefficients, you need the unique coefficient. Any spanning set would not work. You have to have a basis which makes the expression unique. Otherwise, your matrix representation could be different things. That is not permitted.
So in that case, it won't be linear transformation, might not be, right?
So instead of 2379, if I say I want to do it as 237910, for example, if you do something like this, I want to express it in terms of this. Well, this doesn't make sense in the first place. But if you want to write this as C1 this plus C2 this plus C3 whatever this guy, then this C1 C2 C3 will not be unique. That will have multiple solutions. And then which one to choose, there is no canonical choice. But since it is a basis, you will have a solution and it will be unique.
Sir, and just I want to relate it with the later weeks we studied. So are these matrices equivalent or similar? Like what can we conclude about
They
these?
are equivalent. For similarity, you will have to have the basis on the domain and this codomain to be the same. So for example, do I have, so this matrix and this matrix are similar. In this case, they are the same. So it's not saying much. But in general, if you take the same domain for the same basis for the domain and the codomain,
okay,
and you make different choices, like you take beta 1 gamma 1 once and beta 2 gamma beta 1 beta 1 once and beta 2 the second time.
Yeah.
Then the matrices that you obtain, they are similar.
Okay, right. And all these matrices are equivalent, right?
Yes, they are all equivalent.
Okay, got it.
Yeah. See, if you look at this guy, this is the identity matrix. Now that cannot be similar to this matrix because identity matrix is similar only to itself.
Yeah, true.
So similarity will fail. Similarity is a stronger requirement. Yeah. But equivalence will always be there. You can check that all these are rank 2 matrices, for instance.
Yes, okay.
In this particular example. But more generally also, they will all be equivalent.
Got it.
All right. So the final thing that we want to do is kernel and image of linear transformations. In the pursuit of finding whether or not something is injective or surjective, that is what we have been trying to do so far. If a linear transformation is injective or surjective, first we gave an alternative notion of injectivity in the case of linear transformations, where we required that the pre-image of 0 is just 0, nothing more. And we note, okay, at that time I did not say this, but if you collect the set of all pre-images of 0, that is what is called kernel of the transformation. All pre-images of 0, every vector that is mapped to 0 is called the kernel. And that also you can check, it happens to be a subspace. Similarly, and kernel, as we discussed earlier, is related to injectivity of the transformation. Image of T is a set of all vectors injective. If the image is also trivial in the sense that it is the whole space. If the image is also trivial in the sense that it is the whole space. So the trivial subspaces are 0 space and the whole space, right? So kernel needs to be as small as possible. Image needs to be as big as possible. What is as small as possible for kernel? It should always contain 0. It cannot be empty. So the smallest possible set that could be the kernel is the singleton set which contains the 0 vector. So if that is achieved, then it is injective. And image T has to be as big as possible. And as big as possible is the entirety of the codomain. As someone was saying earlier, that if the range is equal to the codomain, then we call it surjective. In other words, if the image, the subspace image of T, if it is equal to the codomain vector space, then we call it surjective. So these are the two subspaces of V and W respectively, which are related to injectivity and surjectivity. Now, how do I find, given a transformation, how do I check whether it is injective or surjective? So once again, we make use of the matrix representation of the transformation. It turns out that the kernel of T is related to the null space of the matrix representation, and the image of T is related to the column space of the matrix representation. So what we are doing is, let me just have this. So you have some data in terms of this, and you get a matrix out of this. So matrix of transformation. So this is whatever transformation is there that is encoded in the matrix of the transformation. And what is that encoding? It is actually given by the basis that you choose to get the matrix of the transformation. So now if I want to find what is kernel T, here the first point, look at the first point, it says that V belongs to kernel T if and only if the coefficient vector of V with respect to beta is in the null space. So coming back to this, if I want to do this, I want to see the null space. Now let us take an example. Let's do R2 to R. By an earlier comment, this should always have some kernel, right? This cannot be injective, is what we had intuitively guessed. So let me take x comma y is x plus y. Just by observation, you know that this thing has a kernel, which is exactly the line y is equal to minus x. Now, what is the matrix representation of this? What is the size of the matrix representation of this?
One cross two.
It's a 1 cross 2. So let's just take the basis, this 1, 1, 1 minus 1, just for convenience. And what is the basis for R? What does it mean to say what is a basis for R?
Like one or any real number can be basis for R.
Any non-zero real number.
Yeah.
Will be a basis for R. So let's take 1 itself. Now if I take 1, 1, 1 minus 1, so what is the image of the first vector? That is 2. And what is the image of the second vector? That is 0. And with respect to this, it is just 2, 0. This might be a stupid example, but let's just go through with it. We'll take some R2 to R2 or R3 to R3 later and see. Now this is the matrix with respect to beta and gamma. What is the null space of this? How do I compute the null space of this? I convert it to REF, and the REF of this is just this. What are the pivots? There's only one pivot. So how many dependent variables? How many independent variables?
One dependent and one independent.
Yeah. So the nullity is equal to 1 of the matrix. So the fact is that the nullity of the matrix is the same as the nullity of the transformation. What is the nullity of the transformation? That is the dimension of the kernel. And if I have to find out a basis for null space of A, how would I do it? In this case, it's just x1 plus 0, x2 is equal to 0. So x1 is equal to 0 is what you get. I'm not doing the steps because I'm assuming you would do it. X2 is equal to t. So the general solution would be this. Do you agree?
Yeah.
So the null space of this matrix, let me call this guy as A. Null space of A is points of the form 0, t, where t varies in R. But then if I look at 0, t and I substitute it in the transformation, do I get 0?
No.
You don't get 0. Why? Because this is encoded information. Like when we are going from the transformation to the matrix, we have done an encoding, which is writing it in terms of the coordinates. So these are not, so this 0, t, the vectors of the form 0, t are not the vectors which are in the kernel, but these are the coordinates of the vectors. So if I want to recover the vectors, what I have to do is write the vectors for which these are coordinates, meaning I have to use these as coefficients. I have to use the vectors that I get as coefficients and write it in terms of my basis, which I use to encode. So I have to come back to the transformation using the same basis. So it's 0 times 1 minus 1 plus t times 1, 1. And in all of these things, the order of the basis is important. I have specified that it's the ordered basis. So what I get is points of the form t, t. T comma minus t, sorry. And that happens to be the kernel of this.
If there is more than one element, like we should substitute them as well and we will get different form, is it?
What do you mean by
Nullity
more
of
than one
A,
element?
like if there is x1, y1 and x2, y2, then we should substitute both of them and we get two different forms, right? Here we have only 0, t, so we just substituted that. If there is one more coordinate in the nullity of A, like
the null space of A, the number of coordinates in the null space of A will be exactly equal to the number of basis elements over here.
oh,
Because
okay.
the null space of A is what? It will have coordinates as many as the variables in your equation, Ax equal to 0.
Yeah.
And that is equal to number of columns of the matrix of the transformation. The number of columns of the matrix of the transformation is in turn equal to the dimension of the domain.
Okay. Okay.
Are you following that?
I mean, like I was asking, similar to like we have something 0, t, like this is considered to be x1, y1, and we will have x2, y2 in some other case. The null space can be span of two vectors.
The null space could be span of two vectors, yes.
Yeah, in that case, even the second one we will substitute and we will obtain some other point. Is it? When I say second,
Yes. Okay. So yeah, earlier I was saying that you do 0, 1, right? So you do that itself. Or let's take this one as the final example of this thing. Let's take, let's say 4 cross 3 with the 2. That should be fine. So suppose I have x1, x2, x3, x4 is equal to t of. I'll just take something simple so that I hope that I'll get All right. So I just want 3, right?
Yeah.
Sorry?
No, like
Yeah,
that's
yeah,
what.
yeah. Okay. So the matrix of this transformation will be a 3 cross 4 matrix. And it will probably have just one element, yeah?
Yeah, again the null space will be one.
Yeah, okay. So let's just take x2, x2, or x1 plus x2, x3, x3. All right. Simple example, but what we want is just the principle of how to do it. So I'll take E1, E2, E3, and let's say the final vector, instead of taking E4, I'll take it as this. This is not the standard basis, and let me just call this guy V4. All right, what is the matrix of the transformation with respect to this basis? How do I calculate? What is T of E1?
It's 1 0 0 0. 1 1 0 0.
1 0 0. Yeah, I need to give a basis for the codomain as well, right? So for the codomain, I'll keep it as standard. Note that this E1, E2, E3 is in domain. This one is not the same as this.
Sorry, sir. That R3 you have to make it as R2, right? Otherwise, the null space will again be only 1, right? Because it's R4.
Not
to
always.
R3.
R4 to R3, not always,
Yeah.
not always. So for example, if I have R4 to R3, as just every vector goes to 0, the null space is the whole space. So that is the extreme. Now I can have things in between also. The thing is, I can never have it to be trivial. That is what was one of the comments that was made earlier, that if you have a higher dimensional space to a lower dimensional space, you cannot have injectivity. So that we'll see later. But for now, let us continue with this. We'll see whether in this case we'll get to 1 or 2 as the nullity. Okay, so T of E1 is just 1 0 0, and this is just E1. T of E2 is 1
It's the
0
same.
0 again.
Yeah.
So this is also E1. T of E3 is
0 1 1.
0 1 1. So this is E2 plus E3 in the codomain. And T of, in this case, the fourth vector, you see it's V4.
2 1 1.
It's 2 1 1. Yeah. 2 1 1. And then that I can just write it as 2 E1 plus E2 plus E3. So what is the transformation? The matrix of the transformation? It's a 3 cross 4 matrix. It's 1 0 0 1 0 0 0 1 1 and 2 1 1. These are just the coefficients of this. Now, if I do the REF, there's only one step to do really. What are the pivots? It is this and this, right? What is the basis for null space of A? Let me call this guy A. How do I compute? What are the independent variables?
X2,
X2, X1, X4.
X2 and X4, right? So X2 is equal to 1, X4 is equal to 0. This is one case. And then X2 is equal to 0, X4 is equal to 1. What is the solution in this case? You have X3 plus X4 is equal to 0 because of the second equation. So x3 is also equal to 0.
x1 will be -1.
-1 plus 1 plus 0 plus 0. Yeah. Verify that this happens. -1 you said, right?
Yeah.
X1 would be -1.
So the solution is -1, 1, 0, 0. This is one of the basis vectors. And in this case, what will x4 is 1, meaning x3 will be -1.
And x1 will be -2.
Will it be -2 or yeah. -2, 0, -1, 1. So this is the other thing. So the basis for this is -1, 1, 0, 0, and -2, 0, -1, 1. Now, if you just look at null space of A, this does not contain vectors which are even in the kernel of T. If you substitute, will you get that? The first one is, but that is just coincidence. But the second one is not, right?
Yeah, we will get -2, -1, -1.
Yeah. So what do we need to do? You have to realize that these are just coordinates of the vectors. They are not the vectors. So if you have the coordinates of a vector, how do you recover the vector? I write -1 times E1. So let me call this guy as some V1 prime, something like that. -1 E1 plus 1 E2 plus 0 E3 plus 0 V4. Because I used this basis to get the matrix. So I have to use this basis to get the vector from its coordinates. And what is this? In the standard form, it will be -1, 1, 0, 0. So that's why you see that the first one was not just a coincidence that it worked. But for the second vector, you have -2 times E1 plus 0 times E2 plus -1 times E3 plus 1 times V4. So what is this? You will get -1, 1, 0, 1, I think. Is this correct?
Yeah.
Yeah, just verify that this thing is correct. But yeah, it is correct, because when you substitute it back over here, what was it? -1, 1, 0, 0. -1, 1, 0, 0. If you look at that, it is in the kernel. So a basis for the kernel would be this and this. A basis for the null space would be the coefficient vector of this in that basis. So when you are trying to find the basis of the kernel, what you do is you go to a matrix. The matrix is formulated with respect to a certain basis. So you'll probably get different matrices when you're using different bases. So how to calculate the null space of a matrix is something that we know. We do that thing. And the basis that you get for the null space is not exactly the kernel of the transformation, but it is the coordinates of the vectors in the kernel of the transformation. So you have to recover those vectors back using the same basis. So use the basis to go to the matrix, compute its coordinates, and come back to the thing using the same basis. Is that fine?
Yeah.
So I did not quite understand this.
Okay, so if I'm given a vector in a vector space with a basis, let's say whatever, v1, v2, vn, what does it mean? It means that I can write v as summation ci vi uniquely. So this C1, C2 up to Cn, this is what I call the coordinates of this vector or the coefficient vector for this vector. So you see what we are doing over here in the beginning is looking at images of the basis vectors and writing their coordinates as the columns, right? Writing their coefficients as the columns. That is how you get the matrix representation. And then you do the familiar thing with the matrix where you just reduce it and then find the null space of that matrix. The basis for the null space you get is not vectors in the kernel, but it is coordinates of the vectors in the kernel. Now, if I tell you C1, C2, Cn is the coordinate vector of some vector with respect to some basis, how will you get that back? You'll just plug this back to get this, right? Now, if I say 1, 1 and 1, minus 1, let's just do this thing. This is a basis, and 2, 0 is a vector in R2. Now 2, vector 2, 0, the vector, how can it be written as 1, 1 plus 1, minus 1? What is the linear combination?
1, 1 and 1.
So this is 1, 1, right? So 1, 1 are the coordinates of coefficients of 2, 0 in this basis. Let me call this guy beta. In beta. Now if I tell you 2, 3 are the coordinates of some vector v in beta with respect to beta, it should not be in beta, but fine, okay. With respect to beta, then what are the coordinates of v? How will you recover that? What does it mean to say 2, 3 are the coordinates? It means that they are the coefficients with respect to this ordered basis, which means that v is 2 times 1, 1 plus 3 times 1 minus 1. So what would that be? 5 minus 1. So given a vector, how do you express it in terms of a basis is one side of the thing. And the reverse is given the coefficients, how do you get the vector back? That is the easier part actually. You just write this times the first vector, this times the second vector. And you will get the vector whose coefficients are these. So when you're doing the null space also, what you get once you convert the data into a matrix form, from the transformation you come to a matrix using a basis. What you're working with is coordinates now. So the answer also you get are the coordinates of the vector. So to recover the vector from its coordinates, what you do is you multiply each coefficient, the first coefficient with the first basis vector, the second coefficient with the second basis vector, and so on. Is that fine?
Sir, like if A is a isomorphic, then we have nullity to be always 0, is it? Like only one element is there, like T of 0?
Yes, because if it's an isomorphism, then it is injective. No? It is at least, as in that is necessary condition.
Yeah, in that case, how will the basis for this null space will be obtained? Like it will be 0, 0, 0, is it? Like only one element?
Yes, you will get only one element. So if it's an isomorphism, first of all, you will have a square matrix representation. We had seen, right? You have to have the dimension to be equal. And then you will have an invertible matrix, which means your RREF will look like this. REF, you might have something over here. RREF will look like the identity, it will be the identity matrix.
Okay.
Which means that you don't really have independent variables.
Yeah.
And the unique solution is just 0.
And here, when we are evaluating this null space, when we have two independent variables, we are alternatively giving 1, 0 and 0, 1. So why
Yes.
is it because of the dimension? Otherwise, if there is only one variable, we are just giving 1 only, right? Not with the 0, we are not getting any solution.
So the aim is to get linearly independent vectors. So if there is just one independent variable, you can just put it as 1. But if you have 2, then you'll have to do, so suppose in this case, you'll get something like this 1, 0, and the second vector will be something like this 1, whatever x1 and x3 are. These will never be dependent to each other. Now, if you have more also, if you do 1, 0, 0 for one thing, 0, 1, 0 for one thing, and 0, 0, 1 for one thing, those things will never be linearly dependent. So that is why we are going for this, so that we get a basis.
Okay, in one independent variable, if we provide 0, then it will be dependent. That's why they are not giving like that.
Yes, if you write everything in terms of if you put 0, then the dependent things will also become 0. So you'll just get the trivial vector.
Yeah. Thank you.
Yeah, and the last thing is
Sorry.
yeah, go ahead.
The vector that you found last by the coefficients, that is the kernel, is it?
So these two vectors, right? These two vectors form a basis for the kernel. Okay, kernel of T is span of V1 prime and V2 prime. So here you have a basis. You recover the vectors. They will be a basis for the kernel. So the kernel itself will be linear combinations of these.
So always basis is coefficients, is it? Sorry, I'm getting a little confused with these things.
That's okay. Where
You were saying the bases are just coefficients that we need to plug back to get the vectors, right? So
yeah, so when you're working with the matrix of a transformation, you are doing something with respect to the basis, and what you're getting is the coefficients. So and to recover the actual vectors, you have to do the reverse operation, which is find the vector for which this is the coefficient.
So the other one is basis of null space, or how differently we name it?
This is just basis of kernel of T. So basis of okay, just one more. So you have null space of the matrix of the transformation is isomorphic to kernel of T. This is an isomorphism where you can send these basis elements to their corresponding vectors. Or if you want to go from here, you just write every vector its coordinate vector. Or if you want from the coordinates to convert to kernel, you just substitute back in using the basis. So this is an isomorphism. So basis of the null space corresponds to basis of the kernel. Kernel is a subspace, right?
Okay, so null space is the coefficient vectors and the kernel is the reversed vector.
Yes. Because see, here we are dealing with. Okay, I'll not say that. I'll not make that. That might be probably more confusing. So let's leave it at that. Now you start with the kernel. You express the vectors in coordinates. Get the matrix with respect to certain basis. Get the information from there, and then that will again be in terms of coordinates. So you, in order to come back to the vector space, you substitute using the basis. Similar thing you can do for image. But for image, what you have to do is calculate the column space of the matrix of the representation. Once again, if you look at the column space, the vectors in the column space will be coordinates of the vectors. The similar thing holds, but over there you just do it with the column space. So here, just like I said, null space of A is isomorphic to kernel of T. Column space of A is isomorphic to image of T. And that isomorphism is exactly given by the coordinate representation of the vectors. I don't think I have time for an example. It took longer than I anticipated. And as a result, we have this ready that rank T plus nullity T is dimension of V. Why is that? Rank T is the same as rank of the matrix. Nullity of T is the same as nullity of the matrix. Even though the spaces may not be the same because we get different vectors, the number of elements is the same, right? You have the basis of nullity of basis of null space of A. Whatever number of elements it has, the basis of the kernel also will have the same number of elements. So rank T and nullity of T, which is dimension of the image of T and the dimension of the kernel of T, respectively. These things add to the number of columns in the matrix representation, which is actually equal to dimension of V. So that is the rank nullity theorem for transformations. And that is the last topic. And yeah, just to give closure on that earlier exercise, saying that if I have a transformation, let's say from R3 to R2, did you say smaller to lower or lower to higher? I'll just do one, it is fine. Now, rank of, suppose this is T, rank of T plus nullity of T is equal to dimension of V. What is dimension of V? That is just 2. If it is injective, so you said that this cannot be surjective, right? The claim was this cannot be surjective.
Yeah, it cannot be surjective.
Yeah, if it is surjective, what would be rank of T? Rank of T, remember, is dimension of image of T. If it is surjective, image of T is the whole space, whole of the codomain.
So it will be 3 in that case, right?
Yeah, it will be 3. So that cannot happen. Nullity cannot be -1. So this is not possible. Cannot be surjective. That intuitive observation now has a proof. Similarly, if you have R3 to R2 or bigger dimensional space to a smaller dimensional space, work with this and let me know if you have any problem. So this is for, I just did it for 3 and 2. You can do it in general for whatever n and m and n is less than m is less than n. There you cannot have nullity to be more than some number or rank to be. It'll be a similar argument. I'm sure you can figure it out. And if not, yeah, let's discuss that tomorrow. I think we'll stop over here. This is, for the first time, not a very easy concept. And it seems like you have the standard basis most of the time. Why do you even want different matrix representations and make it unnecessarily complicated? But this, it has its advantages. Certain basis. So even in the example that we did, we saw that we got the matrix representation as identity. Here I did not make any smart choice. It just so happened. But you want the matrix representation to be as simple as possible for reasons that you'll see in further courses. So making smart choices of basis will give you simpler representation and hence simpler calculations later on. So that's just why do we do this? Answer to a why do we do this question. Do the problems, it might be sort of confusing in the beginning, but yeah, you'll get used to it. All right, are there any doubts?
So any instruction for quiz 2, like how to manage time?
Nothing in particular. I don't have anything like that. You look at the total number of points, look at the total time duration, your ration, how much time you should spend on each question based on how many points it carries. Do the easy ones first. All of these things are general
So I think
instructions.
it should. So I think it should be at least